Tonight, we're going to talk about something that doesn't fit neatly into any category we have for large things in the universe. Not a star, not a nebula, not even an ordinary galaxy. What we're talking about is a structure so extreme that when astronomers first measured it, they assumed something had gone wrong. They checked the instruments. They ran the numbers again. The results kept coming back the same. Phoenix A is real, and it is unlike anything else we have ever found. Let's start with the black hole at its center. Most large galaxies have a supermassive black hole sitting at their core. Our own Milky Way has one. It weighs about 4 million times the mass of the Sun. That number sounds enormous, and by human standards, it absolutely is. But the black hole at the center of Phoenix A weighs 100 billion solar masses. Not 4 million, not 40 million, 100 billion. That is 25,000 times more massive than the black hole at the center of our entire galaxy. It is, as far as we can determine, the most massive black hole ever confirmed anywhere in the observable universe. And some physicists believe it may be sitting right at the theoretical limit of how massive a black hole can actually get. Then there's what Phoenix A is doing. Most galaxy clusters of this size and age are quiet. Their star-forming days ended billions of years ago. The gas that once collapsed into new stars has either been used up or heated beyond the point where it can cool down and form anything. Astronomers call these systems red and dead. Phoenix A should be red and dead. It's old enough. It's massive enough. Every model we had said it should have stopped making stars long ago. But Phoenix A is currently forming around 740 new stars every single year. Our galaxy forms roughly one. That means Phoenix A is building new stars at 740 times the rate of the Milky Way, inside a system that by all rights shouldn't be building any at all. And then there's the size. Phoenix A has a diameter of about 360,000 light years. The Milky Way is around 100,000 light years across. Light takes 100,000 years to cross our galaxy from one edge to the other. To cross Phoenix A, that same beam of light would need more than 360,000 years. It is 3.6 times wider than the galaxy we call home. Everything we know, every star our telescopes have ever resolved into something individual and distinct, exists inside a galaxy that Phoenix A would swallow more than 3 times over. So tonight's video is really about 3 questions. The first is how big Phoenix A actually is, and what that scale means when you try to hold it in your mind alongside things you already understand. The second is how something this extreme comes to exist at all. A galaxy cluster old enough that it should have gone quiet, still burning with the violence of a system in its prime. A black hole so massive it sits at the edge of what physics says is even possible. Something built it, and the answer turns out to be stranger than most people expect. The third question is what Phoenix A tells us about the universe itself. Because when an object breaks this many rules at once, it doesn't just give astronomers something to marvel at. It forces them to go back and look at the rules. We're going to go through all of it. We'll cover the physical dimensions, the black hole, the event horizon, the jets, the star formation, the gas cooling at the core, and what all of it means for how we understand the largest structures the universe has ever produced. By the time we're done, you're going to have a genuine sense of what Phoenix A is, not just as a collection of large numbers, but as something that actually exists out there in space, 5.86 billion light years away, doing things no other object we've ever found is doing. But before we can understand what Phoenix A really is, we need to start somewhere familiar. Let's start with something simple. The sun. It rises every morning. It lights up the sky. It keeps everything on this planet alive. From down here on the surface, it looks manageable. a bright disk you can cover with your thumb if you hold it up at arm's length. That makes it feel small. It isn't. Stretching across roughly 864,000 miles, the sun's width is almost incomprehensible. That number doesn't mean much on its own, so let's put it in terms of something we can actually picture. If you lined up Earth side by side across the face of the sun, you'd need 109 of them just to cross it. The sun's volume is harder to absorb. You could fit approximately 1.3 million Earths inside it. Every mountain range, every ocean basin, every city ever built, every person who has ever lived. Everything resides on a world whose total volume represents less than 1/1,000,000th part of what fills the sun's interior. Within that massive sphere resides 99.86% of everything making up our solar system. Every planet, every moon, every asteroid, every comet, every particle of dust drifting between the worlds. All of it combined makes up the remaining 0.14%. That is how completely the sun dominates everything around it. And yet the sun is ordinary. By astronomical standards, it ranks as a G-type main sequence star, a yellow dwarf, medium mass, medium brightness, medium temperature. There is nothing remarkable about it by the standards of the universe. There are hundreds of billions of stars like it in the Milky Way alone, billions more in every other galaxy we've ever observed. The sun is not special, it just happens to be ours. This is the first stretch the mind has to make. Something as enormous as the sun, a sphere of plasma 864,000 miles across containing more than 1,000,000 Earths, is average. It's the baseline. It's what we mean when we say a star is unremarkable. That should already feel a little disorienting. Hold on to that feeling because we're just getting started. Now scale up. The sun is one star. The Milky Way contains somewhere between 200 and 400 billion of them, not 200 billion suns packed tightly together, spread across a structure roughly 100,000 light years in diameter. A light year is the distance light travels in a single year, moving at 186,000 miles per second. Light can circle the entire Earth 7.5 times in 1 second. At that speed, it still takes 100,000 years to cross the Milky Way from one edge to the other. Think about that. The fastest thing in the universe, traveling for 100,000 years just to get from one side of our galaxy to the other. The Milky Way has a structure to it, a dense central bulge packed with older stars, a flat disk of spiral arms where most of the star formation happens, a diffuse outer halo of ancient stars and globular clusters. Our solar system sits about 26,000 light years from the galactic center, out in one of the spiral arms. We are not in any special location. We're in the suburbs of an average galaxy. The mass of the Milky Way is hard to pin down exactly, but estimates put it somewhere around 1 trillion solar masses when you account for all the stars, gas, dust, and dark matter holding it together. At the center sits a supermassive black hole called Sagittarius, a star, with a mass of about 4 million suns. That sounds enormous. It is enormous. We'll come back to that number later because it's going to become a reference point that helps calibrate something much larger. Here's the next stretch. The Milky Way is one galaxy. Astronomers estimate the observable universe contains roughly 2 trillion galaxies. 2 trillion. Some are smaller than ours. Many are comparable. Some are significantly larger. They are scattered across a web of cosmic structure, filaments and walls and voids, spanning 93 billion light years in every direction from where we sit. The Milky Way is one point in that web, one galaxy among 2 trillion, each containing hundreds of billions of stars. Each of those stars a sun in its own right. Our brains didn't develop to process numbers like this. We evolved to track animals across a plain, to estimate distances in miles, to count things we could hold. The scales we're building toward now are not things any human being has ever experienced directly. They're abstractions, mathematics standing in for something the imagination can't fully reach. That's not a failure of intelligence. It's just an honest account of the limits of a mind that grew up on a small planet. So before we go any further, hold the measuring stick we've just built. The Sun, stretching 864,000 miles across, with room inside for 1.3 million Earths, controlling 99.86% of our solar system's total mass. The Milky Way, 100,000 light-years across, up to 400 billion stars. One galaxy among 2 trillion in the observable universe. These are our reference points. These are the units we'll be measuring with when Phoenix A comes into view. The Milky Way is our home, and by any human measure, it is incomprehensibly large. And yet it's one of the smaller players in this story. Before we can talk about Phoenix A itself, we need to understand the environment it lives in. We've spent some time building up a sense of scale. The Sun, the Milky Way, 100,000 light-years of stars and gas, and that's just our home galaxy. But galaxies don't exist in isolation. They exist in groups, and the largest of those groups are called galaxy clusters. A galaxy cluster is exactly what it sounds like. A collection of galaxies bound together by gravity, sometimes hundreds of them, sometimes thousands, all orbiting a common center of mass. But the galaxies themselves are almost a footnote. The real bulk of a cluster isn't in the stars. It's in 2 invisible components. The first is dark matter, which provides the gravitational scaffolding holding the whole structure together. The second is hot gas, a vast diffuse atmosphere of superheated plasma filling the space between the galaxies. This gas can reach temperatures of tens of millions of degrees. It glows in X-rays. It outweighs all the stars and all the galaxies combined. A galaxy cluster isn't a collection of galaxies floating in empty space. It's a single enormous object, and the galaxies are just the visible fraction of it. The Phoenix cluster is one of those objects. Its official designation is SPT-CLJ 2344-4243. It sits in the southern constellation Phoenix, which is how it got its name. The cluster was first detected in 2010 during a large survey of the southern sky. The telescope doing that survey was the South Pole Telescope located in Antarctica. The South Pole is one of the better places on Earth to do millimeter wave astronomy. The atmosphere there is cold and dry, and that matters because water vapor absorbs the wavelengths you're trying to study. The survey covered about 2,500 square degrees of sky. That's a large patch, but still a small fraction of the full celestial sphere. The detection method is worth explaining. Astronomers weren't looking for Phoenix directly. They were looking for a subtle signature called the Sunyaev-Zeldovich effect. Here's how it works. Galaxy clusters are filled with that hot gas we mentioned. When light from the cosmic microwave background, the faint afterglow of the Big Bang, passes through a cluster, the hot electrons in the gas scatter it slightly. They shift the photons to higher energies. This leaves a faint imprint on the microwave background, a slight change in temperature across that patch of sky. It's a very small effect, but it scales with the total mass of the cluster, which means it's a reliable way to find the biggest, most massive clusters in the universe, regardless of how far away they are. The Phoenix cluster showed up as a strong signal. When astronomers followed up with X-ray telescopes and optical instruments, they found something extraordinary. The Phoenix cluster is about 5.86 billion light-years away. That number deserves a moment. 1 light-year is roughly 5.9 trillion miles. Multiply that by 5.86 billion, and you're looking at a distance that exceeds any normal intuition about space. But the distance isn't just a measurement of how far away the cluster is. It's also a measurement of how far back in time we're looking. Light travels at a fixed speed. The light we're currently collecting from the Phoenix cluster left that cluster 5.86 billion years ago. The universe is about 13.8 billion years old. That means when this light began its journey, the universe was roughly half its current age. Our solar system didn't exist yet. The sun hadn't formed. The Earth was still more than 1 billion years away from existing. And the light from the Phoenix cluster was already traveling toward us. There's something worth sitting with here. When that light departed the Phoenix cluster, humans were not even a remote possibility. There was no solar system, no Earth, no biology of any kind in this corner of space. The light crossed billions of light years, arrived at a planet that hadn't existed when the journey started, and was collected by instruments built by creatures who had only understood electromagnetism for a couple of hundred years. That's the situation with essentially everything we observe at cosmological distances. The cluster itself contains around 1,000 galaxies. Total stellar population across all of those galaxies is estimated at roughly 3 trillion stars. That's 3,000 billion stars, gravitationally bound in the same enormous structure. For reference, the Milky Way contains somewhere between 200 and 400 billion stars. The Phoenix cluster holds somewhere in the range of 10 Milky Ways worth of stars across 1,000 separate galaxies, in addition to all the dark matter and hot gas that dwarfs all of them. It is by any measure one of the most massive galaxy clusters we've ever found. At the center of that cluster is a galaxy called Phoenix A. In clusters this size, the most massive galaxy tends to accumulate near the gravitational center. It pulls in matter, absorbs smaller galaxies over time, and grows into what astronomers call a brightest cluster galaxy, or BCG. Phoenix A is the BCG of the Phoenix cluster. It sits at the bottom of the gravitational well. Everything in the cluster is to some degree falling toward it. Gas flows inward. Galaxies drift toward the center over billions of years. The BCG of a massive cluster is typically one of the most massive individual galaxies in the observable universe, and Phoenix A is no exception. And at the very center of that cluster, dominating everything around it through sheer mass and gravity and the violence of its own existence, sits Phoenix A. Phoenix A has a diameter of about 360,000 light-years. That number doesn't mean much on its own. Numbers that large rarely do. So let's build it up from something you already have a sense of, the Milky Way. Our galaxy is roughly 100,000 light-years across. That's a number astronomers throw around casually, but it represents a distance so vast that light itself, traveling at 186,000 miles per second, needs a full 100,000 years to cross it from one edge to the other. The Milky Way contains somewhere between 200 and 400 billion stars. It is, by any reasonable human standard, an incomprehensibly large structure, and Phoenix A is 3.6 times wider. If light takes 100,000 years to cross the Milky Way, it takes more than 360,000 years to cross Phoenix A. Not 360,000 miles, not 360,000 years at some leisurely travel speed. At the speed of light, the fastest anything in the universe can move, over 1/3 of a million years, just to get from one side to the other. Think about what that means in terms of the stars living inside this galaxy. A star on one edge of Phoenix A and a star on the opposite edge are separated by a distance that light cannot close in less than 3.5 human civilizations worth of time. If you measured civilizations by how long it took ours to get from cave paintings to radio telescopes. They exist inside the same galaxy. They're gravitationally connected to the same structure, and they will never, in any meaningful sense, interact with each other. Now, there is a galaxy that gets brought up whenever Phoenix A's size comes into question. IC1101 is a supergiant elliptical galaxy in the Virgo constellation. In pure diameter, it dwarfs Phoenix A. IC 1101 stretches out to a radius of around 2 million light-years. Its total span can reach 4 million light-years, depending on where you draw the outer boundary. So why isn't IC 1101 the center of this conversation? Because size alone isn't the whole story. IC 1101 is enormous, but it's a quiet system. Its outer regions are incredibly diffuse, very old, very dim, very spread out. It's a galaxy that is essentially wound down. The term quiet system in astronomical parlance means IC 1101 has largely exhausted its reservoirs of gas for new star formation, representing an endpoint in galactic evolution. It has consumed its smaller neighbors over billions of years and settled into an ancient dormancy. Phoenix A, by contrast, is anything but quiet. The density, the activity, the violence happening at its core, all of that sets it apart from simply being a large smear of old stars. A sprawling, inactive giant tells one story. An active furnace of creation tells an altogether different one. That said, 360,000 light-years is still an extraordinary physical scale. When astronomers measure a galaxy's isophotal diameter, they're tracing the outer boundary where the light drops below a certain threshold of brightness. At that edge, you're not in the dense central regions packed with stars and glowing gas. You're in the sparse outer halo where stars are scattered thinly and the distances between them stretch out enormously. Phoenix A's 360,000 light-year diameter includes all of that: the blazing central regions, the surrounding stellar population, the vast dim halo extending far out into intergalactic space. The gravitational reach of a galaxy this size is correspondingly enormous. It doesn't just contain its own stars, it pulls on everything around it. Here's a way to make that concrete. Our Milky Way has satellite galaxies. The large and small Magellanic Clouds orbit us at distances of around 160,000 and 200,000 light-years respectively. Andromeda, our nearest large galactic neighbor, sits about 2.5 million light-years away. These are the landmarks of our local neighborhood. Now imagine Phoenix A sitting where the Milky Way sits. The large Magellanic Cloud, at 160,000 light-years out, would be well inside Phoenix A's outer edge. The small Magellanic Cloud, too. Both of them, entire galaxies in their own right, would be subsumed into Phoenix A's structure, not orbiting it from outside, but embedded within it. Andromeda, at 2.5 million light-years, would still be beyond Phoenix A's boundary. But the Triangulum galaxy, smaller and closer, might sit right at or near the edge. The dwarf galaxies that orbit the Milky Way, and there are dozens of them, would all be gone, consumed into the mass of something far larger. Our entire local group, that spans a few million light-years and contains more than 50 galaxies of various sizes, would be dominated by Phoenix A in a way that's hard to overstate. Phoenix A wouldn't just replace the Milky Way in that picture, it would redefine the neighborhood. What does it feel like to exist inside a galaxy this large? We can only speculate since we experience exactly one galaxy from the inside. But consider that from our position in the Milky Way, roughly 26,000 light-years from the galactic center, we already can't see the core directly, too much gas and dust in between. In Phoenix A, a star at the same proportional distance from center would be about 95,000 light-years out. The rest of the galaxy would extend another 85,000 light-years beyond it in every direction. The scale of the structure around that star would be staggering even by the already staggering standards of galactic astronomy. And then there's the question of what occupies all that space. 3 trillion stars spread across a structure 3.6 times wider than the Milky Way. Stars forming at a rate that hasn't been recorded anywhere else. Hot gas permeating the space between them, glowing in X-rays, cooling and falling inward. The sheer volume of material contained within Phoenix A's boundaries is almost impossible to hold in your head as a single quantity. You keep having to break it down, compare it to something smaller. Even then, the comparisons feel inadequate. But all of that, the 360,000 light-year span, the 3 trillion stars, the X-ray glow, the gravitational dominance over everything around it, all of that is just the container, and the size of the galaxy is almost secondary. This was because what sits at its center is where things get truly strange. At the center of Phoenix A sits a black hole with a mass of 100 billion suns. Let that number sit for a moment. Not 100 suns, not 100 million suns, 100 billion. To understand what that means, we need to start with what a solar mass actually is. One solar mass is the total mass of our sun, roughly 2 septillion kilograms, a number so large it's essentially meaningless to state directly. The sun is already a body so massive that it contains 99.86% of everything in our entire solar system. Every planet, every moon, every asteroid and comet and grain of dust between the worlds, all of it together adds up to less than 1/4% of what the sun weighs. That's one solar mass. Phoenix A's black hole contains 100 billion of them. To build toward that number, start at home. At the center of the Milky Way sits our own supermassive black hole called Sagittarius A star. Astronomers spent decades confirming it was there, tracking the orbits of stars near the galactic center, watching them swing around an invisible point at speeds that made no sense unless something extraordinarily massive was sitting there. What they found was a black hole with a mass of about 4 million suns. 4 million solar masses. That's already an almost incomprehensible figure, and Sagittarius A star is considered a fairly typical central black hole for a galaxy our size. It's not unusual, it's not a record holder. It's just the one that happens to be ours. Confirming Sagittarius A star took decades because black holes emit no light. Astronomers tracked nearby star orbits and velocities. Only one conclusion fit. Something massive and invisible sat at the galactic center. Now multiply that by 25,100. That's how much more massive Phoenix A's black hole is compared to Sagittarius A star. Not twice as massive, not 10 times, not 100 times. 25,000 times more massive. If Sagittarius A star is a large boulder, Phoenix A's black hole is a small mountain range. The comparison barely works. The difference in scale is large enough that they almost belong in separate categories entirely. But there's a step in between. For a while, the largest known black hole was a distant quasar called TON 618. TON 618 has a mass of about 40.7 billion suns. That was already staggering, roughly 10,000 times more massive than Sagittarius A star. A black hole so large that astronomers had to revise what they thought was physically possible. The discovery of TON 618 pushed theoretical upper limits for black hole mass upward. It forced a rethink of how massive these objects could become. The discovery challenged theoretical limits of black hole growth and formation. Astronomers wondered how such massive objects could accumulate so much material in cosmic time. The mechanisms of mergers and accretion seemed suddenly insufficient to explain observations. And then Phoenix A came along with a mass of 100 billion suns. TON 618 suddenly looked like the smaller one. Phoenix A's black hole is more than twice as massive as TON 618, twice the mass of what had previously seemed like an almost impossible object. There's another way to frame this, and it might be the most disorienting comparison of all. The Milky Way galaxy, our galaxy, with its 200 to 400 billion stars, its spiral arms stretching 100,000 light-years across, its vast clouds of gas and dust, its dark matter halo. the accumulated mass of everything that makes up our entire galactic home, has a total mass estimated at somewhere around 700 billion to 1 trillion solar masses, depending on how you measure it. Phoenix A's black hole by itself accounts for roughly 15.4% of that. One black hole, not a galaxy, not a cluster of thousands of stars, a single point of concentrated mass containing something close to 1/6 of everything the Milky Way is made of, measured in one place, at one location inside another galaxy. In one perspective, if you gathered every star humans can see without a telescope and combine their total mass, Phoenix A's black hole would still exceed it. The black holes at centers of other large galaxies pale by comparison. Phoenix A's stands as an extreme outlier, nearly unmatched in the entire observable universe. Think about what that means for the environment around it. Black holes don't just sit passively in the centers of galaxies. Their gravity shapes everything nearby. The more massive the black hole, the farther its influence reaches. For a black hole of 100 billion solar masses, that influence extends across distances that are genuinely difficult to express. The gravitational reach of a black hole isn't a hard boundary. It's a gradient, a slow tightening. But the region where Phoenix A's black hole meaningfully dominates the motions of surrounding gas and stars is vast. Entire star clusters orbit within its gravitational grip. Gas falls toward it from enormous distances, heating up as it spirals inward, radiating energy across the electromagnetic spectrum. The black hole doesn't just live at the center of Phoenix A. It defines what the center of Phoenix A is. Everything around it is organized by its presence. What makes this hard to accept on some level is that black holes aren't made of anything exotic. They're just mass. Ordinary matter compressed beyond a certain threshold, past the point where any known force can prevent further collapse. A stellar mass black hole forms when a massive star exhausts its fuel and its core collapses. A supermassive black hole in principle forms through the same physics, scaled up enormously and accumulated over vast spans of time through mergers and accretion. The physics doesn't change, only the quantity of mass involved changes. And yet, when you accumulate enough mass in one place, 100 billion times the mass of the Sun, the result is something that bends space and time across distances larger than some galaxies. It's the same basic phenomenon that produces black holes a few times the mass of the Sun, just carried to an extreme that seems almost like a different thing entirely. Astronomers use the term ultramassive to distinguish black holes at this end of the scale from merely supermassive ones. The terminology exists because supermassive. That already sounds like the largest possible category turns out not to be enough. Objects like TON 618 and Phoenix A required a new word. They sit at the far edge of what the known universe has managed to produce, the result of billions of years of growth through feeding and merging in the densest, most extreme environments that cosmic structure formation can create. Phoenix A's black hole didn't get to 100 billion solar masses easily or quickly. It got there because it sat at the center of one of the most massive, most active galaxy clusters ever found, in an environment that kept feeding it material at extraordinary rates. And yet here it is, one object, sitting at the center of one galaxy. A single object, not a galaxy, not a cluster, just one black hole, containing 15% of what an entire galaxy is worth in mass. The event horizon of Phoenix A's black hole has an estimated diameter of 590 billion kilometers. Take a moment with that number. Not 590 million. Not 590 billion miles. 590 billion kilometers. That's 366 billion miles across. These are numbers that don't connect to anything in ordinary experience. Our brains didn't develop to handle quantities like this. So let's build toward it slowly, because the scale here deserves that. Start with the solar system. The distance from the Sun to Pluto, the farthest recognized object in our outer solar system, is roughly 5.9 billion kilometers. That's already a staggering distance. Light traveling at 300,000 kilometers per second takes about 5.5 hours to cover that span. When the New Horizons spacecraft flew past Pluto in 2015, the signal confirming the closest approach took 4.5 hours to reach Earth. That's how far Pluto is. That's the outer edge of the familiar solar system. The event horizon of Phoenix A's black hole is 100 times wider than that distance. Not 100 times wider than Earth's orbit, not 100 times wider than Mars. 100 times wider than the full diameter of the entire solar system measured out to Pluto. If you place this black hole where the Sun currently sits, its event horizon would extend 100 times farther than Pluto in every direction. Mercury would be inside it. Venus would be inside it. Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all inside it. The asteroid belt, the Kuiper belt, the scattered disk of icy debris beyond that, all of it swallowed inside the boundary. There would be nothing left outside. Every object we have ever launched a spacecraft toward, every planet every human has ever looked up and seen in the night sky, every moon, every ring system, every comet we have tracked, all of it would exist within the interior of this one object's point of no return. That's what the event horizon actually is. It's not a physical surface. There's no wall there, no barrier you could see or touch. It's a mathematical boundary, the point at which the escape velocity equals the speed of light. Inside the event horizon, to escape the gravitational pull of the black hole, you would need to travel faster than light, and nothing can do that. So nothing escapes. Light itself, once it crosses that line, curves back inward. It cannot get out. From outside the event horizon, you would never see anything that fell past it. The light from that object simply never reaches you. It bends back, falls inward, gone. This is true of every black hole. What makes Phoenix A's event horizon so disorienting is purely the scale. Sagittarius A star, the black hole at the center of our own galaxy, has an event horizon with a diameter of roughly 24 million kilometers. That's already larger than our Sun, which spans about 1.4 million kilometers. Sagittarius A star's event horizon is about 17 times wider than the Sun. That's large. TON 618, which held the black hole mass record before Phoenix A, has an event horizon around 66 billion kilometers across, already enormous. Phoenix A's is 590 billion kilometers. That's almost 9 times wider than TON 618's event horizon. That's 420 times wider than Sagittarius A stars. That's 420 times wider than an object that is already 17 times larger than the Sun. Stack those multiplications. The Sun to Sagittarius, a star to Phoenix A. Each jump is almost incomprehensible on its own. Together they exceed anything our intuitions were built to handle. Now think about crossing it. Not falling through the event horizon, which you could theoretically do without immediately noticing. The boundary itself is invisible, unmarked. But imagine circling the outer edge of it, tracing the circumference at the speed of light. Light travels at 299,792 kilometers per second. In 1 second, it circles the Earth 7.5 times. In 8 minutes, it reaches us from the Sun. In about 5.5 hours, it crosses the entire solar system out to Pluto. To travel around the outer circumference of Phoenix A's event horizon at the speed of light would take 71 days and 14 hours, more than 2 months. moving at the fastest speed anything in the universe is physically permitted to reach, just to trace the edge of the boundary, not to cross the interior, not to explore the surrounding accretion disk, just to circle the perimeter once. The Sun, for comparison, has a circumference that light crosses in about 14.5 seconds. Phoenix A's event horizon circumference takes 71 days. That's roughly 421,000 times longer. There's a reason this particular object keeps producing numbers that feel broken. At 100 billion solar masses, the black hole at Phoenix A's center is near the theoretical upper limit for how massive a black hole can grow, given what we understand about accretion physics and feedback. The event horizon scales with mass. Double the mass, double the event horizon diameter. So 100 billion solar masses produces an event horizon 100 billion times larger than a one solar mass black hole. The scale compounds. That's why the event horizon ends up bigger than the entire solar system. That's why it takes light 2 months just to circumnavigate it. Think about what it would mean for our solar system to sit inside that boundary. Every planet you've ever read about, every spacecraft we've sent out into the dark. Voyager 1, now about 23 billion kilometers from the Sun, still inside the event horizon by a wide margin. The Oort cloud, the distant spherical shell of comets surrounding us at the very outermost edge of the solar system, extending perhaps 2 light-years out, much of it would be inside the event horizon as well. There would be no outside. The entire context in which every human civilization has ever existed, every astronomical observation we've ever made of nearby space, all of it would be interior to this one object, and the boundary itself would be invisible. That's the quiet part of this. No surface glowing red, no physical barrier, just a mathematical line where the geometry of space-time curves so sharply that forward motion only ever points inward. Cross it, and you can keep moving, keep looking around, keep experiencing time for a while. But the future only points one direction, and that direction is toward the center. The event horizon is the most extreme threshold we know of in nature. Phoenix A's is the largest one we've ever found, not by a small margin. By a factor that makes everything we've previously called enormous feel like a reference point for something far beyond enormous. Traveling at the speed of light, the fastest anything in the universe can move, it would take you over 2 months just to trace the outer edge of this black hole's point of no return. The obvious question is how something this massive actually gets built. We've established that Phoenix A's black hole weighs 100 billion solar masses. That number doesn't tell you anything on its own. Numbers that large don't mean anything until you start asking where they came from. So let's ask. The universe is roughly 13.8 billion years old. Phoenix A's black hole is estimated to have formed somewhere between 10 and 100 million years after the Big Bang. That's extraordinarily early. The universe at that point was a completely different place. It hadn't had time to build complex structures. There were no mature galaxies yet, no solar systems, no heavy elements to speak of, just hydrogen, helium, and a small amount of lithium compressed into clouds, starting to collapse under gravity for the very first time. And somehow, in that infant universe, something began forming that would eventually reach 100 billion solar masses. The problem is that this shouldn't be easy. Growing a black hole takes time and fuel. A black hole grows by pulling in matter, gas, dust, other objects, from its surroundings. This process is called accretion. Material falls toward the black hole, forms a disk as it spirals inward, heats up to extreme temperatures, and eventually crosses the event horizon. But accretion has a natural speed limit. There's a rate, called the Eddington limit, beyond which a black hole can't easily consume more material. The radiation pressure from infalling matter becomes so intense that it pushes new material away. The black hole, in a sense, starts choking on its own meal to grow to 100 billion solar masses within the age of the universe, let alone in the time available before Phoenix A's current epoch, requires either feeding at the Eddington limit almost continuously or something else happening alongside it. That something else is mergers. Galaxies don't exist in isolation. They interact. They collide. When two galaxies merge, their central black holes don't immediately combine. They sink toward each other through a process called dynamical friction, gradually losing energy as they interact with surrounding stars and gas. Eventually, they get close enough that gravitational wave emission carries away the remaining energy, and they merge. The resulting black hole is roughly the sum of the two. Do this repeatedly over billions of years across hundreds or thousands of mergers as a galaxy cluster assembles itself, and you can build something very large. This is almost certainly part of how Phoenix A got to where it is. Galaxy clusters like Phoenix A's host cluster form through repeated mergers of smaller clusters and groups. Every time two systems combine, their central black holes have a chance to eventually follow. But mergers alone probably aren't enough. The numbers don't quite work. Even accounting for every merger, you still need the seed black hole to start massive, and you need sustained accretion on top of that. This brings up one of the more interesting debates in modern astrophysics. Where did the first black holes come from? The standard story is that massive stars live short, violent lives and collapse into black holes when they die. The most massive stars, 100 times the mass of the Sun or more, can produce black holes of tens of solar masses when they go. These are stellar mass black holes. They're real. We've detected them. But they start small. Growing a stellar mass black hole to 100 billion solar masses in the time available is an enormous challenge, even with continuous accretion and mergers. So some researchers have proposed a different origin entirely. In the early universe, before the first stars even formed, conditions might have allowed massive clouds of gas to collapse directly into black holes, bypassing the stellar phase altogether. These are called direct collapse black holes. The idea is that under the right conditions, high temperatures, specific radiation environments that prevented the gas from fragmenting into smaller clumps, a cloud of gas containing tens of thousands or even hundreds of thousands of solar masses could collapse straight into a single object. This produces a much heavier seed, not tens of solar masses but potentially millions. A seed that massive has a significant head start. It can grow through accretion and mergers to extraordinary sizes in a time frame that actually makes sense. Astronomers haven't confirmed direct collapse black holes yet, but the existence of objects like Phoenix A's central black hole makes a strong case that something like this must have happened. Now, here's where things get interesting. For a long time, theorists believed that black holes had a practical upper mass limit of around 50 billion solar masses. The reasoning was based on feedback. As a black hole grows, it becomes more luminous. It ejects more energy into its surroundings. That energy heats the surrounding gas. Hot gas doesn't fall in as easily. The black hole essentially starts fighting against its own growth. Beyond a certain mass, the feedback becomes so powerful that accretion slows to almost nothing. The black hole starves itself. 50 billion solar masses was considered close to that ceiling. Then astronomers found TON 618, a quasar with a black hole weighing about 40.7 billion solar masses. That pushed the known boundary. And then came Phoenix A, 100 billion solar masses. That's roughly double what was previously thought possible. It didn't just approach the old limit, it blew past it. When astronomers reported this measurement, it required revising the theoretical models. The upper mass limit had to be reconsidered. And when researchers worked through the updated physics, they arrived at a new figure, around 100 billion solar masses, which happens to be almost exactly where Phoenix A sits. That's not a coincidence most physicists are comfortable ignoring. The feedback mechanism is the key. A black hole this massive generates radiation and jets of material on a scale that is genuinely hard to overstate. Those jets push into the surrounding gas with enormous force. They heat it. They drive it away from the center. At some point, the black hole simply can't get enough cold gas to keep growing at any significant rate. The fuel supply is cut off not by external factors, but by the black hole's own output. Growth slows. Then it slows more. Then it effectively stops. The system reaches something approaching equilibrium, and the black hole is frozen at whatever mass it managed to accumulate before that happened. This is why Phoenix A's black hole is so scientifically significant. It didn't just set a new record, it may have revealed where the record ends. A black hole that weighs 50 billion solar masses could theoretically keep growing. The feedback wouldn't be overwhelming yet, but at 100 billion, the physics suggest you're approaching a point where further substantial growth becomes self-defeating. The energy output required to accrete new material becomes the same energy output that prevents new material from falling in. The process terminates, or at least reduces to something negligible on any meaningful timescale. We don't know for certain that 100 billion solar masses is the absolute ceiling. The universe is enormous, and we've surveyed a small fraction of it. There could be exceptions. There could be environments we haven't found where the feedback dynamics work differently. But the theoretical case is strong, and the fact that the largest black hole we've ever confirmed sits right at the theoretical limit is hard to dismiss. Physicists now believe that 100 billion solar masses may represent a genuine ceiling, not just the largest we've found, but potentially the largest that physics will allow to exist. Here is where Phoenix A stops being merely large and starts being genuinely inexplicable. Everything we've covered so far, the size of the galaxy, the mass of the black hole, the scale of the event horizon, all of that is extreme, but it follows a kind of logic. Big things can form. Big black holes can grow. The universe has had 13 billion years to build structures, and some of those structures ended up enormous. That's strange, but it's a strangeness we can trace. What comes next doesn't follow the same logic. What comes next is where the story stops making sense. Phoenix A is forming stars at a rate of roughly 740 solar masses per year. The Milky Way, our galaxy, forms about one new star per year. Sometimes a little more, sometimes a little less, but the figure is close to one. Phoenix A is forming the equivalent of 740. In the time it takes our galaxy to build a single star, Phoenix A builds a small city of them every year, without stopping. That number alone would be remarkable for any galaxy. For Phoenix A, it's almost offensive, because Phoenix A shouldn't be doing this at all. To understand why, you need to understand what star formation actually requires. Stars don't form from hot gas. They can't. Hot gas moves too fast, its particles bouncing and colliding with too much energy for gravity to pull them together. For a star to form, you need cold, dense gas, material that is slowed down enough that its own gravity can take over, drawing it inward, compressing it, heating it until nuclear fusion ignites in the core. Cold gas is the raw material. Without it, there are no new stars. Galaxy clusters are filled with gas, enormous quantities of it. But that gas is hot, extraordinarily hot. We're talking tens of millions of degrees, sometimes hundreds of millions. Gas at these temperatures glows in X-rays. It doesn't collapse. It doesn't form stars. It just sits there, radiating, filling the space between galaxies like an invisible sea of superheated plasma. Young galaxies have cold gas. They use it to build stars, and they build stars rapidly. You can see this in the early universe, galaxies blazing with star formation, burning through their raw material at furious rates. But over time, things change. The cold gas gets used up. What remains gets heated. The massive black holes at the centers of these galaxies pump energy into their surroundings through jets and radiation, keeping the gas warm, preventing it from cooling back down. The star formation slows. It stops. The galaxy grows quiet and red, its light dominated by old, cool stars rather than bright young ones. Astronomers have a name for galaxies that have reached this state. They call them red and dead. And galaxy clusters that have grown as massive and as old as the Phoenix cluster should be red and dead. That's not a guess. That's what the models predict. That's what we see in other clusters of comparable mass and age. The cold gas is gone. The star-forming days are over. The cluster just sits there, slowly evolving, adding no new stars worth mentioning. Phoenix A does not care about this prediction. When astronomers first started examining the Phoenix cluster in detail, something kept coming back wrong. The central galaxy was too bright. Not just a little too bright, dramatically, conspicuously too bright. And the brightness wasn't coming from old stellar populations the way you'd expect in a red and dead system. It was coming from young stars. Hot, blue, newly formed stars scattered through the center of a galaxy that had no business forming them. The Chandra X-ray Observatory is what really opened this up. Chandra is designed to detect X-ray emissions, which means it can map where hot gas is concentrated throughout a cluster. When astronomers pointed it at the Phoenix cluster, they found something that didn't match the picture they expected. The X-ray emission from Phoenix A was the most luminous ever recorded from a galaxy cluster. More X-ray output than any other known massive cluster. That alone tells you something unusual is happening. There's an extraordinary amount of hot, energetic gas packed into this system. But here's where it gets strange. When they looked at the data more carefully, they found that the gas near the center of the cluster wasn't staying hot. It was cooling, and it wasn't cooling slowly. The cooling rate measured was 3,820 solar masses per year. That is the highest cooling rate of hot gas ever recorded in a galaxy cluster. It isn't close. Nothing else we've found approaches it. Think about what that means. Every year, gas equivalent to the mass of 3,820 suns is shedding energy, dropping in temperature and sinking toward the center of this cluster. Gas that was tens of millions of degrees is cooling down. And cool gas, as we just established, is exactly what you need to make stars. The connection between the cooling rate and the star formation rate isn't coincidental. The cooling gas is falling inward. It's concentrating at the center. It's reaching temperatures where it can collapse. And it's collapsing into stars by the hundreds every year. The star formation rate of 740 solar masses per year is the downstream result of a cooling process operating at almost 5 times that scale. A huge fraction of what cools doesn't form stars immediately. Some of it gets consumed by the black hole. Some of it gets heated again by the energy the black hole releases. But enough of it gets cold enough and dense enough that stars ignite, and they ignite constantly. The mystery at this stage is why. Other clusters have hot gas. Other clusters have massive central black holes that pump energy into the surrounding medium. In those clusters, the heating wins. The black hole's jets keep the gas warm, the cooling slows down, and the star formation stays suppressed. That feedback loop between the black hole and the surrounding gas is one of the most well-established mechanisms in galaxy evolution. It's supposed to work. It works almost everywhere we look. In Phoenix A, it isn't working, or rather, it isn't working fast enough. The cooling is outpacing the heating by a substantial margin. The gas is losing energy faster than the black hole can put it back in. Something about the balance here, the density of the gas, the rate at which the black hole is feeding, the geometry of how the energy gets deposited, has tipped in a direction we don't normally see. And the result is a galaxy cluster that looks nothing like what its age and mass would predict. This is the point where the story becomes a detective problem. You have an object that is, by every reasonable measure, one of the oldest and most massive structures of its kind that we know about. It should be inactive, quiet, its star-forming days long past. Instead, it's producing hundreds of new stars every year, surrounded by cooling gas at the highest rate ever recorded, with a black hole at its center that is feeding actively and growing. Something is maintaining this system. Something is keeping the cold gas flowing. Something is feeding this machine, and for a long time, nobody could agree on what. The gas that fills galaxy clusters is hot, extraordinarily hot, tens of millions of degrees, glowing in X-rays. Not warm, not heated. Tens of millions of degrees. That's hotter than the interior of most stars. It's a plasma so energetic that it doesn't emit ordinary light at all. It radiates in X-rays, which means it's invisible to the human eye and invisible to optical telescopes. You need instruments specifically built to detect high-energy radiation to even know it's there. The Chandra X-ray Observatory is one of those instruments, and when astronomers pointed Chandra at the Phoenix cluster, what they saw changed how they understood the entire system. The hot gas in a galaxy cluster isn't static. It's constantly radiating energy outward. Every second, photons carry energy away from the gas and out into space. When gas loses energy, it cools. When it cools, it contracts. When it contracts, it gets denser, and denser gas radiates even faster. It's a self-reinforcing process. The gas near the center of the cluster, where the density is highest, cools the fastest. It sinks inward. More gas flows in behind it to fill the space. That inward drift of cooling gas is what astronomers call a cooling flow. In most clusters, cooling flows exist, but they're modest. The gas cools slowly. The central black hole compensates by firing jets that pump energy back into the surrounding gas. The jets heat the gas faster than it can cool. The system reaches a kind of rough balance. Star formation stays suppressed. The cluster sits quiet. In Phoenix A, that balance doesn't exist. The cooling rate in Phoenix A is 3,820 solar masses of gas per year. That's not a typo. Every year, the equivalent of 3,820 suns worth of hot gas cools down and flows toward the cluster center. That number is the highest cooling rate ever recorded in any galaxy cluster. It's not slightly higher than the next competitor. It's in a different category entirely. The gas is losing energy so fast and flowing inward so quickly that no feedback mechanism has been able to keep up with it. Chandra detected this by mapping the X-ray emission across the cluster. Hot gas glows brightly in X-rays. Gas that is cooled somewhat glows differently, at lower energies, with a different spectral signature. By mapping those differences in detail, astronomers could trace where the gas was hottest, where it was cooling, and where the coolest material was concentrating. The coolest gas in the cluster was sitting right at the center, exactly where you'd expect a cooling flow to deposit it. The data was unambiguous. Something was driving an enormous river of cooling gas toward the heart of Phoenix A. Now here's why that matters. Stars don't form from hot gas. Hot gas resists gravity. The thermal pressure inside superheated plasma is enormous, and it pushes outward against any gravitational force trying to compress it. You can't squeeze a cloud of 10 million degree gas into a star. The physics won't allow it. What you need is cold gas. Dense, Cold gas. Gas that has lost enough energy that gravity can win. Gas that can collapse into clumps, and those clumps can contract further, and eventually the pressure and heat at the center becomes high enough to ignite nuclear fusion. That's how a star is born. The cooling flow in Phoenix A is delivering cold gas to the cluster center at 3,820 solar masses per year. Some fraction of that gas keeps cooling until it's cold enough to collapse. And when it collapses, you get stars. Hundreds of them every year. The star formation rate we talked about before isn't some separate mystery. It's the downstream consequence of the cooling flow. The two numbers are connected directly. The cooling flow is the pipeline. The star formation is what comes out the other end. Think about that chain for a moment. Hot gas, tens of millions of degrees, fills the cluster. It radiates X-rays, loses energy, and cools. It sinks toward the center. At the center, the densest and coolest material collapses under gravity. Stars ignite. Meanwhile, the black hole at the very center is pulling in some of that same gas, adding 60 solar masses to its own mass every year. And as it feeds, it fires jets. Those jets push back against the inflow, heating some of the surrounding gas, inflating cavities in the plasma. Some of the cooling flow gets disrupted, some gets heated back up, some keeps falling inward anyway. It's not an orderly process. It's chaotic. Gas is cooling in some regions while being reheated in others. Jets are punching outward through material that's simultaneously collapsing inward. Stars are forming in dense filaments while the surrounding plasma is still millions of degrees. The whole system is a violent churning equilibrium, or something close enough to equilibrium that it's persisted for millions of years without destroying itself entirely. But the key point is this. In Phoenix A, the cooling is winning. The gas is coming in faster than the jets can push it back. The Chandra data shows the coolest gas concentrated at the center, not dispersed by jet heating. The star formation rate, 740 solar masses per year, is only possible because the cooling flow is supplying raw material faster than any feedback mechanism is removing it. In a typical massive cluster, this doesn't happen. The black hole grows large enough, its jets become powerful enough, and eventually the feedback wins. The cooling slows. The star formation stops. The cluster goes red and dead. That's the standard story. That's what should have happened in Phoenix. Long before we ever pointed a telescope at it. Other clusters show signs of partial cooling flows, but the jets suppress them before they can run away. The balance holds. Astronomers had actually built that balance into their models of how massive galaxy clusters evolve. The feedback loop was considered one of the reliable mechanisms in astrophysics. Not ironclad, but robust. Something that worked consistently across the clusters they had studied in detail. Phoenix A broke that assumption cleanly. The cooling rate of 3,820 solar masses per year is so far above anything seen elsewhere that it's not a marginal exception. It's a different regime entirely. The jets from the central black hole are real. They're energetic. They're doing what jets do in other clusters. But they're not enough. The cooling flow has overwhelmed them. There's still genuine uncertainty about why. Maybe the black hole grew large enough that its jets, despite their scale, are geometrically misaligned with the densest cooling regions. Maybe the gas supply is so enormous that even efficient jet heating can't cover the full volume. Maybe there's something about the structure of this particular cluster, the density profile of the gas, the mass distribution, the geometry of the infall, that made the cooling flow unusually difficult to suppress. Astronomers have proposals. No single explanation has been confirmed. What is confirmed is the result. In Phoenix A, for reasons that still aren't fully understood, that balance broke, and the gas started losing the fight. Blasting outward from the central black hole in opposite directions are two enormous jets of plasma, radio-bright streams of material accelerated to a significant fraction of the speed of light. These jets were detected by the Australia Telescope Compact Array, a network of radio dishes spread across New South Wales. Radio telescopes pick up emissions that optical telescopes can't see, and what they found around Phoenix A was striking: two bipolar structures extending outward from the active nucleus, forming a shape that astronomers describe as diffuse and bar-like at larger scales. The jets stretch somewhere between 30,000 and 65,000 light-years from the central black hole. To put that in perspective, the entire Milky Way is about 100,000 light-years across. These jets are already half that length, and they're still relatively young. Young by cosmic standards, anyway. Astronomers estimate the jets are roughly 10 million years old, based on how fast they're expanding through the surrounding gas. If they're moving at approximately the speed of sound in the cluster medium, then the math puts their age at around 10 million years. There are also signs of even younger jets closer to the nucleus, compact radio structures suggesting a second, more recent episode of activity, perhaps just 1 million years old. So the black hole hasn't fired once and gone quiet. It keeps firing. That matters, because the effect these jets have on the surrounding gas is not what you'd expect. In most galaxy clusters, jets like these are the reason star formation shuts down. That's the standard picture. A massive black hole sits at the center of a cluster. Gas cools. It falls inward. The black hole feeds. It generates jets. Those jets push outward into the surrounding hot gas, depositing enormous amounts of energy. The gas heats back up. It stops cooling. It stops forming stars. The whole system reaches a kind of equilibrium. The black hole essentially acts as a thermostat, keeping the cluster gas too warm to collapse. It's called AGN Feedback, and it's considered one of the most important processes in regulating how galaxies grow. It's why most massive old clusters are red and dead. Phoenix A has jets, so Phoenix A should be red and dead. And yet, it isn't. When astronomers combined data from the Chandra X-ray Observatory with radio observations and optical imaging from Hubble, something unexpected emerged. The jets in Phoenix A aren't just heating the surrounding gas, they're also carving out cavities in it. As the jets push outward, they inflate bubbles in the hot intracluster medium, regions where the gas has been physically displaced, pushed aside. These cavities are visible in Chandra's X-ray images as dark patches surrounded by brighter emission. That contrast is real. Where the jets have pushed, the gas is thinner and less dense. Along the edges of those cavities, the opposite is true. The gas has been compressed. Compressed gas cools faster. That's not complicated physics. Denser gas radiates energy more efficiently, loses heat more quickly, and becomes more susceptible to gravitational collapse. So while the interior of each jet cavity is heated and disrupted, the walls around those cavities become zones of accelerated cooling. Cold gas accumulates along these edges. That cold gas is the raw material for stars, and it's being generated by the very jets that in every other cluster we've studied would have stopped star formation from happening at all. The data from Hubble reinforce this. Filaments of star-forming gas trace the edges of the jet cavities. The distribution isn't random. The new stars aren't spread evenly across the central galaxy. They're concentrated in regions that correspond to where the jets have been pushing. The compression is real, and the star formation is following it. Astronomers combining Chandra, Hubble, and VLA observations concluded that Phoenix A represents the first confirmed case of a black hole actively boosting star formation rather than suppressing it. That had been theorized. Models had suggested it was possible under certain conditions, but Phoenix A was the first system where the evidence was clear enough to confirm it. Think about what that means. Every other massive black hole we've studied at the center of a rich galaxy cluster has been acting as a regulator, putting the brakes on star formation, keeping the system in check. Phoenix A's black hole is doing the opposite. It's pushing gas around in a way that accelerates cooling, feeds star formation, and contributes to the very process that astronomers expected it to be shutting down. That's not a small distinction. It's a fundamental difference in how this system behaves compared to every comparable system we've found. And the black hole is feeding voraciously. Current estimates put its accretion rate at around 60 solar masses per year. Every year, material equivalent to 60 suns worth of mass falls across the event horizon and disappears. The Milky Way's central black hole, Sagittarius A star, accretes a tiny fraction of that, a negligible trickle by comparison. Phoenix A's black hole is consuming at a rate that reflects how much raw material is available. The cooling flow is dumping enormous quantities of gas into the center of the cluster. Some of that gas collapses into stars. Some of it falls into the black hole. Both processes are running simultaneously at rates that have no parallel in anything else we've found. The 60 solar masses per year accreting into the black hole also tells you something about the energy being pumped back into the system. When material falls into a black hole, a fraction of its mass gets converted into energy before it crosses the event horizon. That energy goes somewhere. Some of it powers the jets. Some of it heats the surrounding gas. But in Phoenix A, the heating clearly isn't keeping pace with the cooling. The gas is losing the energy battle. The cooling flow is winning, and the jets, rather than compensating for that by depositing heat uniformly, are channeling their energy in ways that create new cold spots, new compression zones, new sites for star formation. There's something almost paradoxical about this. The black hole is the most massive ever found. It's consuming 60 solar masses a year. It's generating jets that extend tens of thousands of light years into the surrounding cluster. By any measure, this is a violent, energetic, disruptive object. And yet its net effect on the gas around it appears to be more stars, not fewer. The destroyer and the creator are the same thing here, and the creation is winning. The black hole at the heart of Phoenix A is the most massive we've ever found, and unlike every other black hole of comparable scale, it appears to be making the star formation problem worse, not better. To understand where Phoenix A sits in the hierarchy of extreme cosmic objects, it helps to line them up. Start with the Milky Way. Our galaxy is about 100,000 light-years across. It contains somewhere between 200 and 400 billion stars. At its center sits Sagittarius A star, a supermassive black hole with a mass of roughly 4 million suns. That sounds enormous. In human terms, it is. But the Milky Way forms about one new star per year. It's a mature, relatively stable system. It's been around for roughly 13 billion years. It's doing what old galaxies do, burning through existing stars slowly, adding very few new ones. By any measure we can apply from the surface of Earth, the Milky Way is a staggering structure. It would take light 100,000 years to cross it from one edge to the other. And yet, in this comparison, it is the baseline, the smallest item on the list. Now put Phoenix A next to it. Phoenix A is 360,000 light-years across. That's 3.6 Milky Ways laid side by side. Its central black hole doesn't weigh 4 million solar masses. It weighs 100 billion. That's not a modest difference. That's a factor of 25,000. The black hole at the center of Phoenix A outweighs the black hole at the center of our galaxy by roughly 25,000 times. And Phoenix A is forming new stars at a rate of 740 per year compared to our galaxy's one. Not twice as fast, not 10 times as fast, 740 times as fast. For a long time, the black hole mass record belonged to something called TON 618. It's a quasar, an extraordinarily bright, active galactic nucleus located about 10.4 billion light-years from Earth. Its black hole weighs about 40.7 billion solar masses. That was the number astronomers pointed to when someone asked how massive a black hole could get. 40.7 billion suns. It seemed like it should be close to a ceiling. And then Phoenix A came in at 100 billion. Not slightly heavier, not edging past the record. More than twice the mass of what had previously held the title. TON 618 didn't come close. Then there's IC1101. If you've spent any time looking at lists of the largest known galaxies, you've seen this name. IC1101 is enormous. Its outer envelope of diffuse stellar material extends roughly 2 million light-years in radius, which makes it far larger than Phoenix A in terms of sheer physical diameter. It sits at the center of a galaxy cluster about 1 billion light-years away. It holds somewhere around 100 trillion stars. By almost any simple measure of physical scale, IC1101 is bigger. But here's what IC1101 is not doing. It is not forming hundreds of new stars every year. Its central black hole, while massive, is not feeding at the rate Phoenix A's is. It is not producing the most powerful cooling flow ever recorded. It is not generating jets that appear to be accelerating star formation instead of shutting it down. IC1101 is enormous and quiescent. It's an old, settled system. Phoenix A is enormous and violent. The distinction matters enormously. This distinction between size and activity represents a fundamental divide in how galaxies and clusters evolve over cosmic history. Most massive systems follow a predictable trajectory. They grow large through mergers and collisions. Their black holes feed on available material, and then they settle into quiescence as their fuel depletes and their jets cool. Phoenix A, by contrast, appears caught in a different evolutionary phase entirely, one where its supermassive black hole remains vigorously fed and actively shaping its environment. This ongoing vigor, sustained over cosmically significant timescales, is what truly sets it apart from other massive structures. The Coma Cluster is another useful comparison. It's one of the densest galaxy clusters we've mapped in detail. It sits about 320 million light-years away. It's massive, containing thousands of galaxies and a vast reservoir of hot gas. But the Coma Cluster is what astronomers call red and dead. Its star formation days are over. The gas is there, but it's too hot to collapse into stars, and nothing is driving it to cool fast enough to change that. The Coma Cluster is what Phoenix A is supposed to look like, given its age and mass. It's the expected outcome. Phoenix A looks nothing like it. So Phoenix A is not just the most extreme object we've found in a single category. It holds records simultaneously. Largest confirmed black hole. Highest confirmed cooling rate in a galaxy cluster. Among the highest star formation rates ever detected in a system of this age and mass. These aren't loosely related properties. They're connected. The black hole feeds the jets push the gas cools and falls inward. The falling gas feeds both the black hole and the star formation. It's a system running at full throttle in ways that other systems, even other massive clusters, simply aren't. Now zoom out further. The Phoenix cluster is one cluster among thousands of known clusters. The observable universe contains something in the range of 2 trillion galaxies. The cosmic web, the large-scale structure of the universe, is built from filaments of dark matter and gas, with galaxy clusters concentrated at the nodes where those filaments intersect. There are superclusters, vast collections of clusters spanning hundreds of millions of light-years. There are voids, enormous regions of near emptiness stretching across similar distances. In this picture, the Phoenix cluster is one node in one filament in one small region of a structure spanning 93 billion light-years. Think about that for a moment. Phoenix A contains 3 trillion stars. The entire Phoenix cluster holds around 1,000 galaxies, and the observable universe contains 2 trillion galaxies. The numbers stop having intuitive meaning at a certain point, but they point in a clear direction. Everything we've described, the 100 billion solar mass black hole, the 360,000 light-year diameter, the 740 stars forming every year, all of it adds up to a fraction of the total that is genuinely impossible to express in any satisfying way. Our brains didn't evolve to process this. We evolved to track animals across open ground, to remember the location of water, to count roughly how many people were in a group. Nothing about that history prepared us to hold in our heads the idea that 2 trillion galaxies exist, each containing hundreds of billions of stars, and that the most extreme single object among all of that is still a speck in the total accounting. And yet Phoenix A stands out. In a universe of 2 trillion galaxies spread across 93 billion light-years, this one object still manages to be the record holder, not just in one measurement but in several at once. Astronomers who study clusters regularly are still pointing at it. The black hole mass, the cooling rate, the star formation rate, none of these have been surpassed since Phoenix A was characterized. There are other large clusters. There are other active galactic nuclei. There are other systems with high star formation rates. Nothing else combines all of it at this scale. Against the full scale of the observable universe, Phoenix A is a single bright point in a web of structure that stretches for 93 billion light-years in every direction. And somehow, it is still the most extreme thing we have found. Imagine, as a thought experiment, that you could travel toward Phoenix A. You start somewhere else in the universe. Billions of light-years of distance separate you from it. At that range, you wouldn't see anything. The cluster would be invisible against the background of space, not dim, not faint, just gone, swallowed by distance. Even with the best instruments we have, Phoenix A appears as a faint, unremarkable smear at the edge of detectability. The universe is a big place, and most of it looks empty from far enough away. But you keep moving, closing the gap. And slowly, something starts to emerge. First, there's a subtle glow in the X-ray spectrum, hot gas. Enormous quantities of it, radiating energy at temperatures in the tens of millions of degrees. This gas cloud alone contains more ordinary matter than all the galaxies inside the cluster combined. Think about what that means. Every star, every planet, every piece of solid material in every one of those 1,000 galaxies, all of it outweighed by diffuse gas you can't even see with your eyes. It stretches across millions of light-years, glowing in wavelengths far beyond what human vision can detect. You're still not close, but the cluster is resolving now. Hundreds of galaxies are becoming distinguishable, bound together by gravity, moving through that hot gas like islands in a glowing sea. Most of them look the way old galaxies look, reddish, elliptical, quiet. Their star-forming days are long behind them. They drift. They glow with the light of aging stars. And then, at the center of all of this, something is different. One galaxy sits at the heart of the cluster, larger than the others, brighter, pulling everything toward it through sheer gravitational dominance. That's Phoenix A. You're looking at it now. It's enormous. An elliptical structure stretching across hundreds of thousands of light-years. No spiral arms, no defined disk. Just a vast, roughly oval concentration of stellar mass, glowing red and infrared, with brightness increasing toward the center. The outer regions are sparse, stars separated by enormous distances, gradually thinning as you move away from the core. But the sheer physical extent of the thing is hard to absorb. Light takes over 360,000 years to cross it from one side to the other. The Milky Way, our entire home galaxy, would fit inside it with room to spare, several times over. And around the main body of the galaxy, there are filaments, narrow, glowing threads of gas and young stars, arcing outward from the central regions and curved structures. Hubble observations have traced these. They're star-forming filaments, streams of cooling gas collapsing into new stars as they go. They look almost delicate against the scale of the galaxy itself. Thin arcs of blue-white light where new stars are being born, curling away from the center. You wouldn't expect to see this in a galaxy this old and this massive, but there they are. 740 solar masses of new stars every single year, being born somewhere along those filaments. The mechanism driving this continuous star formation is not fully understood. Cooling gas is falling inward from the surrounding cluster environment, and under certain conditions, it favors star production in these filamentary structures. Whatever the precise process, it remains unusual for a system this old. Closer now. The central brightness is intensifying. There's a concentration of light at the very core of Phoenix A that signals something active. This is the nucleus. The black hole is feeding. Material is spiraling inward toward the event horizon, compressing and heating as it goes, radiating enormous amounts of energy before it crosses the point of no return. The accretion disk around the black hole is one of the most energetic environments in the observable universe. It's bright across multiple wavelengths: optical, ultraviolet, X-ray. The active galactic nucleus of Phoenix A shares properties with both quasars and Seyfert galaxies. It's genuinely unusual in its behavior. And from the nucleus, blasting outward in opposite directions, the jets. Two enormous streams of plasma accelerated to a significant fraction of the speed of light, punching through the surrounding gas. These jets extend somewhere between 30,000 and 65,000 light-years from the central black hole. They're young, as these things go, around 10 million years old. They're still expanding, still pushing into the gas cloud surrounding them, inflating cavities in the hot intracluster medium as they go. You can trace them in radio wavelengths, bright, linear structures emerging from the nucleus and fading as they spread into the surrounding space. The gas cloud the jets are moving through is almost incomprehensibly large. It extends far beyond the visible galaxy. It's hotter than anything naturally produced on Earth, tens of millions of degrees, glowing in X-rays. And it's being disturbed by those jets, compressed and reshaped where they push into it. In most galaxy clusters, this is where the story would end. The jets heat the gas stops cooling. Star formation shuts down. Everything stabilizes into a slow, quiet decline. But in Phoenix A, the gas is cooling faster than the jets can reheat it. The cooling rate is 3,820 solar masses per year. The jets are losing. The gas keeps falling inward. This imbalance is critical to understanding the system's unusual behavior. In most clusters, balance is achieved quickly and equilibrium settles in. Phoenix A remains far from any such equilibrium. You're close enough now that the scale of the central black hole starts to matter in a different way. You can't see the event horizon. No light escapes from inside it, which means it creates an absence rather than a presence. A region of distorted space where everything bends around a point of no return. Its event horizon has the diameter of 590 billion kilometers, 366 billion miles. If you placed it where our sun sits, every planet in the solar system would be inside it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all inside. The Kuiper Belt, inside. Pluto, inside. The event horizon extends roughly 100 times farther than the distance from our Sun to Pluto. There is no human experience that maps onto this. There's no analogy that fully captures it. The numbers are just very large, and the object is genuinely that extreme. The distortion around it is real, though. Gravitational lensing bends the light coming from objects behind the black hole, warping and stretching images of distant galaxies into arcs. Matter spiraling inward accelerates and heats to extraordinary temperatures. X-rays pour outward from the accretion disk. Radio waves trace the jets. The surrounding gas glows. The filaments of new stars arc outward from the turbulent center. The whole structure, the galaxy, the jets, the filaments, the gas cloud, exists as one interconnected, violent, ongoing process. 100 million years from now, astronomers predict, this will all quiet down. The fuel will run out, or the feedback will finally win, and the star formation will stop. Phoenix A will become what it was always supposed to be, a massive elliptical galaxy, red and dead, with a black hole that has grown even more enormous sitting at its center in stillness. But right now, at this moment in cosmic time, none of that has happened yet. And somewhere at the heart of all of it, invisible but detectable by the violence it creates in everything around it, the black hole, 590 billion kilometers across at its event horizon, feeding, growing, blasting jets of material into a gas cloud the size of a small galaxy. The rate at which Phoenix A is currently building itself cannot last. That's not speculation. That's the conclusion astronomers reached after studying the data from Chandra, Hubble, and the radio observations. The numbers don't add up to something sustainable. They add up to something burning through its fuel at a pace the universe simply can't maintain forever. Think about what's happening right now inside that cluster. 740 new stars are forming every single year. The black hole is pulling in 60 solar masses of material annually. Hot gas is cooling at a rate of 3,820 solar masses per year, pouring inward toward the center, collapsing, igniting. The jets are firing. The whole system is running at full speed. By every metric we can measure, Phoenix A is in a state of violent, almost frantic growth. But the researchers who studied it put a rough limit on how long this can continue. About 100 million years. After that, the system is expected to change. The cold gas reservoir feeding all that star formation will thin out. The black hole's jets will gradually deposit more energy into the surrounding gas. The cooling rate will slow. The pipeline will start to run dry. 100 million years sounds like a long time. Against a human lifespan, it's incomprehensible. Against the age of the universe, it's nothing. The universe is roughly 13.8 billion years old. 100 million years is less than 1% of that. It's a brief episode, a flash. What happens when it ends? Phoenix A will settle into exactly the state it should have been in already. A massive elliptical galaxy at the center of a rich cluster, red and dim, no longer producing stars at any significant rate. The cooling flow will weaken. New star formation will essentially stop. The galaxy will grow old quietly, its existing stars aging and dying over billions of years, its black hole still slowly growing, but no longer at the feverish pace we see today. Astronomers have a term for this: red and dead. It's the natural end state of a galaxy Phoenix A's size and age. Phoenix A just hasn't gotten there yet. This represents an unusual moment in the cosmic timeline. Most galaxy clusters of Phoenix A's size have already cooled and settled by this stage in the universe's history. They exhausted their gas supplies billions of years ago, their brief, intense star-forming phases long since concluded. Phoenix A's extreme activity suggests a system that's either unusually young for its size or unusually rich in available fuel, or both. It's a temporary window of abundance that physics itself will eventually close. What we're observing is a fleeting epoch of intensity. The stars being born right now won't all survive to see that transition. The most massive ones won't last long at all. A star with 20 or 30 times the mass of our Sun burns through its fuel in a few million years. It lives fast and ends violently, collapsing and then exploding as a supernova. Those explosions aren't just spectacular, they're functional. When a massive star detonates, it scatters the heavy elements it spent its life forging, carbon, oxygen, iron, silicon, out into the surrounding gas. That gas gets enriched. The next generation of stars that forms from it carries a slightly higher concentration of heavy elements than the generation before. Phoenix A is doing this on an enormous scale. 740 stars forming per year means a large fraction of those are massive, short-lived stars that will explode within a few million years. Hundreds of supernovae are probably going off inside Phoenix A every year, each one seeding the surrounding gas with heavy elements. Over time, the cluster gas becomes progressively more metal-rich. The chemistry of the environment changes. This matters for what comes after because the composition of the gas affects how it cools, how it collapses, what kinds of stars form from it. So even as Phoenix A winds down, the stars it's creating right now are shaping the conditions for everything that comes next. They're enriching the gas that will eventually stop forming stars. They're contributing to the slow evolution of a system that will outlast them by billions of years. The matter doesn't disappear. It gets recycled. It moves from gas to star, to supernova, back to gas. Changed each time, carrying the record of everything it's been through. There's something worth sitting with in that. The stars forming in Phoenix A today are temporary. The cluster will outlast every single one of them. But the heavy elements those stars produce will still be drifting through that cluster long after the stars themselves are gone. Some of it will end up in future stars. Some will remain in the gas phase indefinitely. The matter keeps moving. It keeps changing form. Phoenix A's current burst of star formation is violent and brief, but its consequences will echo through the cluster's chemistry for a very long time. The black hole will keep growing through all of this, slower eventually, but steadily. Even after the star formation shuts down, the black hole doesn't stop accreting. It just accretes more slowly as less cold gas falls toward the center. Over billions of years, it will grow larger still. The system that was Phoenix A's extreme present will have evolved into something quieter. The jets that are currently pushing through the cluster gas, inflating cavities, compressing cool filaments into stars. Those jets will still fire occasionally, but the scale of the activity will be nothing like what we observe today. Astronomers predict this partly because they've seen the end state in other clusters. There are massive galaxy clusters scattered across the observable universe that went through similar phases early in their histories. They're quiet now. Their brightest cluster galaxies sit at their centers, enormous, metal-rich, passively evolving. No unusual star formation, no extraordinary X-ray luminosity, no record-breaking cooling flows. They did what Phoenix A is doing now, and then they stopped. Phoenix A hasn't stopped yet, but the physics says it will. The extraordinary thing is the scale of what gets produced during this window. 100 million years at 740 stars per year. That's 74 billion new stars added to the cluster during this phase alone. 74 billion. And that's just the stars. That doesn't count the mass accreted by the black hole, the gas scattered by supernovae, the heavy elements distributed through the cluster, the structural changes to the surrounding environment. Phoenix A is leaving a permanent mark on its own future in the span of what amounts to a cosmic eye blink. But for this particular window in cosmic time, 100 million years, which is nothing against the age of the universe, Phoenix A is burning at a rate nothing else we've ever found can match. What makes Phoenix A scientifically important isn't just that it's the most extreme thing we've found, it's that it contradicts what we thought we understood. For decades, astronomers operated with a fairly clear model of how massive galaxy clusters evolve. Young clusters form stars. They burn through their cold gas. Over billions of years, that gas gets heated. Star formation slows. Eventually, it stops. The cluster goes quiet. Red and dead, as astronomers say. The stars that exist keep aging. No new ones replace them. The cluster just sits there, massive and inert, glowing faintly in the infrared. That was the expected endpoint. That was what the physics predicted. And for most clusters we've studied, that's exactly what we see. The model worked. It held up against observation after observation. Astronomers trusted it. Then Phoenix A showed up and the model stopped working. Here's what the model said should be impossible. A galaxy cluster this old, this massive, this far along in its evolution should not be forming 740 stars per year. It should not have a cooling flow dumping 3,820 solar masses of gas inward every single year. It should not have an active nucleus blasting jets into the surrounding gas while simultaneously feeding star formation rather than shutting it down. Every one of those things contradicts what the standard picture predicted. Not slightly, not in a way you can smooth over with an adjustment here or there. Phoenix A is doing all of these things at the same time at record-breaking rates in a system that should be completely quiescent. That's not a small anomaly. That's the model failing. The piece that surprised astronomers most was the cooling flow. In most clusters, the central black hole acts as a thermostat. Gas cools and starts to sink inward. The black hole feeds on some of it. The jets fire. That jet energy heats the surrounding gas back up. The cooling slows. The feedback loop runs, and the cluster stays in rough balance. Hot gas doesn't cool fast enough to form many stars. That balance is what produces red and dead clusters. That balance was assumed to be essentially universal at this scale. Phoenix A has a cooling rate so extreme that the black hole's jets can't keep up with it. The gas is losing energy faster than the jets can replace it. The thermostat is broken. Cold gas is accumulating at the center faster than anything can stop it. And cold gas forms stars. Martin Rees, one of the most prominent cosmologists alive, looked at Phoenix A and said it suggests we need to fundamentally rethink how the most massive galaxies at cluster centers actually grow. That's a significant statement. Rees wasn't saying the model needs a small correction. He was saying the mechanism we assumed was building these giant central galaxies might be wrong, or at least incomplete. The standard view held that central galaxies and clusters grow mostly through mergers, smaller galaxies falling in, combining, adding their stars to the central mass. Gas cooling was considered a secondary process, too slow, too easily suppressed. Phoenix A pushes back hard on that assumption. If the cooling of hot intracluster gas can deposit thousands of solar masses per year into the center of a cluster, and if that cooled gas can collapse into stars at the rate Phoenix A demonstrates, then cooling flows may be responsible for a far larger fraction of stellar mass in brightest cluster galaxies than anyone previously credited. The numbers are not subtle. At 740 solar masses of new stars per year, Phoenix A builds stellar mass at a rate that would double the stellar content of an entire Milky Way in a few billion years. That's not a footnote to galaxy formation. That's a primary driver. What this means for galaxy formation models is that they've been missing something. The most massive galaxies in the universe, the giant ellipticals sitting at cluster centers, may have gotten that way partly through cooling flows that ran hot for limited periods of time. Phoenix A catches us a system in the middle of one of those periods. We've never seen it this clearly before. Most clusters shut it down early. The feedback wins, the gas heats up, the stars stop forming. Phoenix A, for reasons that are still being worked out, never reached that equilibrium. The cooling kept winning. The gas kept falling. The stars kept forming. And we happened to look at it while it was still happening. There's a second implication that connects the black hole to the galaxy. Phoenix A's black hole is 100 billion solar masses. That mass didn't come from nowhere. A black hole that large had to accrete an enormous amount of material over its lifetime. The question of how black holes and their host galaxies grow together has been studied for years. There's a well-documented relationship between black hole mass and the mass of the central bulge of a galaxy. Bigger galaxy, bigger black hole. They seem to grow together. The mechanism behind that relationship isn't fully understood, but Phoenix A offers a clue. If cooling flows feed both star formation and black hole accretion simultaneously, both drawing from the same reservoir of cold gas sinking toward the center, then both the galaxy and the black hole grow together, driven by the same process. Phoenix A is a live demonstration of that co-growth happening in real time. The Phoenix cluster was first detected in 2010. It's been barely a decade and a half since astronomers realized what they were looking at. In that time, it's already rewritten the expected behavior of cooling flows, challenged assumptions about how long star formation can persist in massive clusters, demonstrated for the first time that a supermassive black hole can actively accelerate star formation rather than suppress it, and pushed theorists to expand their models of how the most massive galaxies in the universe accumulate their mass. Every time astronomy finds an object that breaks the existing model, the model gets better, and Phoenix A has broken several at once. Measuring anything at a distance of 5.86 billion light-years is an exercise in creative inference. Phoenix A is not something you can point a telescope at and simply read off its properties. The light we detect today left that galaxy when the universe was roughly half its current age. Our sun didn't exist yet. The solar system hadn't formed. That ancient light has been traveling through an expanding universe for nearly 6 billion years. When it finally reaches our instruments, it carries information, but extracting that information requires methods that are anything but straightforward. Start with the detection itself. Phoenix A wasn't found by looking for it directly. The South Pole Telescope picked it up in 2010 using something called the Sunyaev-Zeldovich effect. Hot electrons in the galaxy cluster distort the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. As that background radiation passes through the cluster, the electrons give it a slight energy boost in some wavelengths and suppress it in others. The result is a characteristic fingerprint in the microwave sky. It's a subtle signal. You're not seeing the cluster at all. You're seeing the shadow it casts on the oldest light in the universe. That's how Phoenix A was found, not directly but by the distortion it leaves behind. Once astronomers knew where to look, they turned other instruments toward it. The Chandra X-ray Observatory mapped the cluster's X-ray emission. Hot gas, tens of millions of degrees hot, glows in X-rays. The pattern of that glow tells you where the gas is concentrated, how dense it is, how fast it's cooling. Chandra can't take a photograph of Phoenix A the way you might photograph a mountain. It's building a picture from photon counts, from spectral analysis, from the spatial distribution of high-energy light arriving at a detector after a 6 billion-year journey. The image that emerges is real, but it's a reconstruction. Every step involves a model, an assumption, an inference built on physics we trust, because it works everywhere else we've tested it. Hubble provided optical and infrared observations. The VLA and the Australia Telescope Compact Array mapped the radio emission, the jets. The lobes of plasma blasted outward from the central black hole. Each of these observatories sees a different piece of the puzzle. None of them sees the whole thing. You stack the data sets, you cross-check them against each other, and gradually a picture assembles. But it's a picture with margins of error built into every measurement. The black hole mass is where this gets particularly difficult. At this distance, you cannot watch individual stars orbiting the central black hole the way astronomers can study Sagittarius A star at the center of our own galaxy. The resolution isn't there. Instead, you use indirect methods. One approach looks at the dynamics of hot gas close to the nucleus, the way it moves. The velocities implied by its spectrum, the gravitational pull required to produce those velocities. Another approach uses scaling relations. Astronomers have found that across many galaxies, black hole mass correlates with properties of the surrounding galaxy, the velocity dispersion of stars in the bulge, the total mass of the stellar structure. You measure what you can measure, plug it into a relationship calibrated on closer, better studied systems. Arrive at an estimate. The problem is that each technique has its own sources of uncertainty. The gas dynamics can be complicated by the jets, by turbulence, by the fact that you're looking at a system in an unusually active state. The scaling relations were built on smaller, quieter black holes. Whether they still hold at 100 billion solar masses is not guaranteed. Different teams applying different methods to the same data can arrive at numbers that differ by a factor of 2 or more. For Phoenix A, estimates of the black hole mass have ranged across a substantial interval. The 100 billion solar mass figure is the most widely cited, but it isn't a single precise measurement. It's a best estimate with real uncertainty attached to it. This is not a flaw in the science. This is how science at the edge of what's measurable actually works. Think about what astronomers are doing. They are determining the mass of an object 6 billion light-years away by analyzing the wavelengths of light that crossed most of the observable universe before landing on a detector the size of a room. The fact that they can constrain it at all, that they can say with confidence this black hole is in a class nothing else occupies, is the remarkable part. Not that the error bars are large, but that there are measurements at all. And here's what doesn't change regardless of where the number lands within its uncertainty range. Even the most conservative estimates place Phoenix A's black hole far beyond anything else we've confirmed. If the true mass turns out to be 70 billion solar masses instead of 100 billion, it's still almost twice ton 618's 40.7 billion. If it's 80 billion, it still contains a larger fraction of an entire galaxy's worth of mass than any other single object we know of. The uncertainty doesn't dissolve the strangeness of this object. It just reminds you that the measurement was never easy, that every number came at the cost of real work. The same caution applies to the galaxy size, the star formation rate, the cooling flow rate, the jet extent. These are all derived quantities. They depend on assumptions about distance, about the physics of the emitting gas, about how light behaves as it travels through an expanding universe. Astronomers who study Phoenix A know this. They report their findings with error bars precisely because the uncertainty is real and it matters. The 740 stars per year figure is an estimate. The 3,820 solar masses per year cooling rate is an estimate. The 590 billion kilometer event horizon diameter is calculated from an estimated mass. But estimates built from multiple independent methods, cross-checked against each other, consistent with what physics predicts and with what every other instrument observing the same object has found, those estimates are not guesses. They are the best available picture of something we can't visit, can't touch, can't see directly. And the picture they paint is consistent across every approach. Phoenix A is in a category by itself. The uncertainty in these measurements is real. Astronomers will keep refining them, but no refinement is going to reduce the black hole at Phoenix A's center to something ordinary. There's a temptation to think of Phoenix A as something utterly foreign, a monster in a distant corner of the universe that has nothing to do with us. Something observed, cataloged, and filed away as an extreme data point in a field of extreme data points. A curiosity 5.86 billion light-years from anything we'd call home. But that framing doesn't hold up. The distance is real. The foreignness is an illusion. Start with the gas. The 740 stars forming each year inside Phoenix A aren't being built from raw, untouched hydrogen left over from the Big Bang. Some of that material is primordial, yes, but a significant portion of it has already been through a star. It was forged, scattered, accumulated again, and now it's collapsing back into something new. That's not unusual. That's how the universe builds things. Stars are not manufacturers of matter, they're processors of it. They take what exists and rearrange it into heavier, more complex forms. When they die, they release those forms back into the surrounding gas. The next generation of stars forms from that enriched material, and the cycle runs again. Every element heavier than helium in the universe came from a stellar core. Carbon, oxygen, nitrogen, iron, calcium. None of it existed at the beginning. The Big Bang produced hydrogen, helium, and trace amounts of lithium. Everything else required the interior of a star, where pressure and temperature reach conditions extreme enough to fuse lighter nuclei into heavier ones. When those stars ended, either quietly, shedding their outer layers, or violently, as supernovae, that material was returned to space. It drifted, it cooled, it mixed with surrounding gas. Eventually, gravity pulled some of it together again, and new stars formed from the remnants of old ones. This process has been running in the Phoenix cluster for billions of years, the progenitor stars that lived and died before Phoenix. A reached its current state, seeded the intracluster gas with heavy elements. The cooling flow that now drives Phoenix A's star formation is carrying enriched material inward, feeding it into the collapse zones where new stars ignite. Those new stars are building themselves partly from the ash of stars that no longer exist. And when those new stars die, the most massive ones within just a few million years, they'll enrich the gas further. The cycle doesn't stop. It compounds. Think about what that means for the atoms in your body. The calcium in your bones was forged in the core of a massive star that died before our solar system formed. The oxygen in every breath you take was processed through stellar fusion and scattered by a stellar death. The iron in your blood traces back to a supernova, a star massive enough to fuse iron in its core before the whole structure collapsed. These aren't metaphors. These are the actual histories of the atoms you're made of. They were somewhere else before they were here. They were inside a star. They were scattered into a gas cloud. They drifted for millions of years and eventually found their way into a collapsing region of the Milky Way that became our solar system, our planet, and eventually us. The Phoenix cluster is running the same process right now. Not a different process, the same one. The 740 stars forming this year in Phoenix A will fuse hydrogen in their cores, generate heavier elements, and eventually scatter that material back into the cluster gas. Some of those atoms will end up in the next generation of stars forming in the same cluster. Some will drift outward into the wider environment. The universe doesn't produce waste, it produces input for the next stage. Consider the larger implication. The recycling of matter that happens in Phoenix A happens everywhere. in every star-forming galaxy, in every cluster, in every corner of the cosmos. The distance between us and Phoenix A is merely spatial. In every other way, we are part of the same system. The same laws of physics govern the processes. Atoms move through the same cycles. What begins in one region of space eventually reaches another. The universe operates as a unified whole, connected not by proximity, but by fundamental rules. We tend to think of ourselves as observers of this process, watchers looking outward at something that operates out there, independently, without connection to us. But that's not the right framing. We're not outside the cycle looking in. We're a product of it. The same gravitational collapse that is producing stars in Phoenix A right now produced our Sun 4.6 billion years ago. The same nuclear fusion reactions happening in Phoenix A's newest stars happened in the stars that died before our solar system formed and gave us the raw material to exist. The mechanism is identical, the scale is different, the distance is vast. But the physics connecting Phoenix A's star-forming regions to the atoms in your hand is not a metaphor or a poetic gesture. It's a literal description of where matter comes from and how it moves through the universe. There's something clarifying about that. Phoenix A isn't an exception to the universe's normal behavior. It's an extreme expression of it. The cooling, the collapse, the fusion, the death, the scattering, the recollapse. That sequence has been playing out since the first stars formed, in galaxies of every size, in clusters near and far. Phoenix A runs it faster and at greater scale than anything else we've found. But the underlying process is the same one that produced you. The 5.86 billion light years between us and Phoenix A isn't a separation from something alien. It's distance between two regions of the same ongoing process. The process is happening in Phoenix A right now, or rather, as they were 5.86 billion years ago when the light we observe actually left, are the same processes that built everything you've ever touched. The natural question, once you've absorbed what Phoenix A is whether something even larger could exist somewhere in the universe. It's the same question that comes up with the largest stars. With Stephenson 218, astronomers asked whether a star could grow bigger. The answer was probably not by much. The same question applies here, and the answer is similar, but not quite as clean. Let's start with what physics actually says. Black holes grow by consuming material. Gas falls inward, heats up, forms an accretion disk, and some fraction of it crosses the event horizon. But as a black hole grows more massive, it gets more luminous. The radiation it produces pushes outward on the surrounding gas. At a certain point, that outward pressure, called radiation pressure, becomes strong enough to slow the infall of new material. The black hole is essentially blowing away its own food supply. This is called the Eddington limit, and it sets a rough ceiling on how fast any black hole can grow. A more massive black hole hits this limit sooner. Growth slows. Eventually, it can stall almost entirely. There's another mechanism working against runaway growth. As we covered earlier, the jets that blast outward from the black hole heat the surrounding gas. Hotter gas doesn't cool as easily. Gas that doesn't cool doesn't fall inward. The black hole starves. In most clusters, this feedback cycle keeps the black hole from growing past a certain threshold. Phoenix A's black hole has beaten that threshold already. It sits at roughly 100 billion solar masses. That is not just a record. According to the physics we currently understand, it may be close to the actual maximum. Astronomers have calculated that somewhere around 100 billion solar masses, the feedback mechanisms become overwhelming. The black hole produces so much radiation and drives such powerful jets that it becomes nearly impossible for any significant amount of gas to reach it. The growth rate drops towards zero. Not because there's no gas nearby, there's plenty in Phoenix A's cluster, but because the black hole itself keeps that gas too hot and too disturbed to fall inward efficiently. It's a self-limiting system. The bigger it gets, the harder it is to get bigger. That theoretical ceiling was already being pushed before Phoenix A Ton 618 came in at about 40 billion solar masses and was considered extreme. Phoenix A at 100 billion doubled it, and then some. And 100 billion is right at the edge of where the physics says the brakes come on hard. It's not a coincidence. The universe may simply not permit much beyond this point, at least not through the accretion processes we understand. But here's the honest part. We've only looked at a small fraction of the observable universe in enough detail to find something like Phoenix A. The South Pole Telescope survey that first detected the Phoenix cluster covered about 2,500 square degrees of sky. The full sky is roughly 41,000 square degrees. We've done deep surveys of portions of it, but not all of it, and not all with the same sensitivity. There are regions obscured by dust in our own galaxy where objects this distant would be difficult or impossible to detect through optical telescopes alone. There are clusters at greater distances still, far enough that even the Sunyaev-Zeldovich signal becomes harder to pull out cleanly. Could there be a galaxy cluster out there with a central black hole at 150 billion solar masses? Or 200 billion? The physics makes it unlikely, but unlikely is not impossible, and our surveys are incomplete. If something like that exists, we haven't ruled it out by finding it and measuring it. We've ruled it out only by not having looked everywhere yet. The universe is also old enough that some of the most extreme systems may have already peaked and faded. A cluster that had a Phoenix A-like phase 5 billion years before Phoenix A would look red and dead today. We'd see a massive elliptical galaxy with a very large black hole, no unusual star formation, no cooling flow, nothing to flag it as extraordinary except the black hole mass itself. Black hole masses are hard to measure at extreme distances. We might have already passed by systems that were once more active than Phoenix A without recognizing what they were. What we can say with some confidence is this. The universe is 13.8 billion years old. For a black hole to grow to 100 billion solar masses, it needs enormous amounts of time and material. Phoenix A's black hole is thought to have formed in the first 100 million years after the Big Bang, and it has been growing since. That's a long head start. Most black holes didn't get that combination: extreme early formation, sustained access to dense gas, a cluster environment rich enough to keep feeding it. The conditions that produced Phoenix A are rare enough that we've only found one. That doesn't mean there isn't another one. It means the odds are against it. And the physics argues that even if another candidate exists, it's probably not dramatically larger. The ceiling that Phoenix A has hit is real. It's written into the equations that govern how radiation interacts with gas, how jets thermalize the intracluster medium, how feedback loops self-regulate over cosmic time. Think about that for a moment. We haven't just found the largest black hole. We may have found the point where the universe runs out of room to make them bigger. Not because of some arbitrary limit, but because of the physics of how black holes feed and how they shut off their own food supply when they get large enough. Phoenix A sits right at that line. Whether it's exactly at the maximum or just close to it, we can't say with certainty. The measurements carry uncertainty. Future telescopes may refine the number, but no refinement is going to move Phoenix A out of this neighborhood. We've found the ceiling, or something very close to it, and it turns out the ceiling was far higher than anyone expected. Think about what it actually means to know all of this. We are on a planet roughly 8,000 miles across. We orbit an average star in an average galaxy. Nothing about our location is special. Nothing about our size is remarkable. We are not at the center of anything. And yet, from this small rocky surface, we have measured a black hole 5.86 billion light-years away. We calculated its mass. We determined its event horizon diameter. We worked out how fast it's consuming surrounding material. We traced the jets firing from its core and estimated how old they are. We detected the cooling rate of gas filling a region of space larger than most galaxies. We did all of that without going anywhere. Think about what that requires. The light arriving at our telescopes from Phoenix A left its source before our solar system existed. The sun hadn't formed yet. Earth didn't exist. There were no oceans, no continents, no atmosphere. The atoms that would eventually become everything on this planet were still drifting through interstellar space in some other galaxy entirely. And the light from Phoenix A was already traveling. It had already been traveling for hundreds of millions of years before the first grain of dust in our solar system stuck to another grain of dust. By the time the sun ignited, that light was more than halfway here. By the time life appeared on Earth, it was most of the way. And eventually, after all of that, it arrived. It landed on a mirror inside a telescope on a planet that hadn't existed when the journey began. And we read it. That's not a small thing. Our brains didn't evolve to process this kind of information. We evolved to track animals across short distances. We evolved to recognize faces, to find food, to avoid things that could kill us. Nothing in our evolutionary history required us to measure the mass of a black hole 6 billion light-years away. And yet here we are, doing exactly that. Using math, using physics, using instruments we built from materials we dug out of the ground, we reached across 6 billion light-years and extracted specific numbers. The black hole weighs 100 billion solar masses. The event horizon stretches 590 billion kilometers across. The surrounding gas is cooling at 3,820 solar masses per year. The star formation rate is 740 new stars per year. The jets are roughly 10 million years old. These are not estimates pulled from nowhere. They come from real data. Real photons that traveled for nearly 6 billion years and hit real detectors on real telescopes, operated by real people sitting at desks. The Sunyaev-Zeldovich effect told us the cluster was there. Chandra's X-ray data told us how hot the gas was and how fast it was cooling. Radio telescopes traced the jets. Hubble captured the filaments of star-forming gas. All of these instruments pointed at the same patch of sky, at the same distant object, and each one revealed a different layer of the same extraordinary thing. None of that is obvious. None of it is guaranteed. There is no law of nature that requires a species on a small planet to develop the mathematics of general relativity, build orbital X-ray observatories, or think carefully enough about ancient light to extract the mass of a black hole from it. That happened because specific people worked on specific problems for long enough that the answers eventually came out. And what came out was Phoenix A. Consider what we actually know about it now. The galaxy itself spans 360,000 light-years. That's 3.6 times the width of the Milky Way. The cluster it anchors contains roughly 1,000 galaxies and 3 trillion stars. At the center of all of that sits a single black hole containing 15% of the total mass of an entire galaxy like our own. Not 15% of one galaxy inside the cluster, 15% of a full Milky Way equivalent packed into one object. The event horizon alone is 100 times larger than the entire distance between the Sun and Pluto. If it replaced our Sun, every planet in the solar system would already be inside it. Every moon, every asteroid, the Kuiper Belt, all of it. Gone before you even started thinking about what was happening. And on top of all that, This object is forming 740 new stars per year. Stars that would each take millions or billions of years to live out their lives. Stars whose eventual deaths will scatter heavy elements into the surrounding gas. Elements that might someday, in some distant future, end up in planets. In some cases, perhaps, in things that are alive. The same chain of events that produced the carbon in your body ran in Phoenix A's progenitor stars billions of years ago. You are not observing this process from outside it. You are a downstream product of it. Stars formed, burned, exploded, scattered material, and that material eventually ended up here, assembled into something capable of pointing a telescope at a galaxy 5.86 billion light-years away and understanding what it sees. That is strange. It is genuinely strange. There is no other word for it. What we know about Phoenix A will keep changing. The measurements we have now carry real uncertainty. Better telescopes will sharpen the numbers. Future instruments will resolve details we currently can only infer. The James Webb Space Telescope and whatever comes after it will push the edge of what we can observe further back in time, further out in distance. There may be things about Phoenix A that we currently have wrong. That's how this works. The model gets revised when new data arrives. But even the most conservative revision of everything we think we know about Phoenix A doesn't change the basic picture. Something that massive, that active, that extreme exists out there. The uncertainty in the numbers doesn't touch that. It's worth sitting with the distance for a moment. 5.86 billion light-years. A light-year is how far light travels in a year, moving at 186,000 miles per second. That's already a number that exceeds anything our intuition can hold. And the distance to Phoenix A is 5.86 billion of those. The observable universe is about 93 billion light-years across. Phoenix A sits roughly a third of the way out from where we are. It is not at the edge. It is not the most distant thing we've ever detected. It is simply the most extreme thing we've found at the distance we could examine it in enough detail to understand what it was. There are almost certainly stranger things further out, things we haven't found yet, things the universe produced in its earliest epochs that we haven't had the instrument resolution to properly characterize. The observable universe contains roughly 2 trillion galaxies. We have examined a small fraction of them in any serious detail. Phoenix A may not be the most extreme thing that exists. It's the most extreme thing we know about so far. That distinction matters. It keeps the question open. What we have right now is this: a galaxy 360,000 light-years wide, anchoring a cluster of 1,000 galaxies, housing a black hole of 100 billion solar masses, producing 740 new stars per year, cooling gas at the fastest rate ever recorded, firing jets 50,000 light-years long from its active nucleus, growing by 60 solar masses of black hole mass every single year. All of it measured from a planet whose entire diameter is smaller than the uncertainty in some of these figures. Phoenix A is out there right now, or rather, as it was nearly 6 billion years ago, making stars, feeding its black hole, blasting jets into the surrounding gas, indifferent to the fact that on a small rocky planet in an unremarkable corner of a different galaxy, some arrangement of atoms that calls itself human has figured out exactly what it is.